In the previous videos in this section, we took a look at how we can go through and graph a function to variables, and then also how to find partial derivatives. One of the outcomes of that is being able to find the equation of a tangent plane to a function at a specific point, and that's what we're going to look at in MATLAB. And so what we're going to do is we're going to find the partials. We're going to substitute values at a specific point into the partials, and then we're going to build the equation of a tangent plane. All right, so I'm going to outline the code as to how we're going to do this from an example I drafted, and then we're going to work through an example of a different function. But let's just consider a really simplistic paraboloid, fx squared plus y squared. And let's consider it the point 2, 1, all right? And of course, if we substituted 2 and 1 back in, it would be the ordered triple 2, 1, 5 by substituting back in. And so here's the code that we're going to use to be able to build this graph of the tangent plane as well as the paraboloid. So first of all, we're going to define a number of symbolic variables, x and y, obviously, because we need to find the derivatives. We're going to substitute back into fx and fy because remember, to find our equation of a tangent plane, we need to substitute into the slope in the x direction, the slope in the y direction. We're going to get the plane itself equation, and then z is going to be the function itself. So we define z as x squared plus y squared. We find the derivatives in terms of x, or with respect to x and with respect to y, right here and right here. However, this function or this expression right here might be a little bit new because we haven't seen this before. We're actually doing the subs function, and we're going to substitute back into fx, which is our derivative, but fx may have might be composed of both x and y variables. So for x, we're going to substitute 2. For y, we're going to substitute 1. So that's the set notation. So we're substituting for the array x, y, and we're going to substitute when x is 2, y is 1. And we do the same thing down here with fy. The equation of our plane is going to be z0, which is this right here. So that's basically going to be the 5, where we plug 2 and 1 back into our function, plus the slope in the x direction, which I call the fx val, which we found up here, and then x minus 2, because that's going to be our x value, and then y minus 1, because that's our y value, times the fy val. And then finally, I just do an easy surf of the function and an easy surf of the plane that we just created, so that way we can plot them both on the same graph. And not only does it graph it, but it finds the equation of the tangent plane. You can see right above here in the graph, really nicely. All right, so saying all that, let's go ahead and find the equation of the tangent plane to this surface, fxy, which is really z, 9 minus x squared minus y squared at the point 2, 2. And then we're going to go ahead and graph the function as well. So, and then also plot its tangent plane. So let's start by defining some sims, and our symbolic variables are x, y, fx, fy, the plane, and z. All right. And then we're going to go ahead and define what z is. So z in this case is going to be the square root of 9 minus x squared minus y squared. And then we can go ahead and find the derivative, fx, which is going to be diff of z with respect to x. And we can also find fy while we're at it, which is going to be equal to the derivative of z with respect to y. Now we can do the substitutions. So we're going to use the subs function, and we're going to substitute, and I'm going to define that as to be our, I'll just call it fx val. I think that's what we called it last time. So we have our fx val, which is going to substitute back into fx. We're going to substitute for the values of x and y. And the values that we're going to substitute in are 2 and 2. And we get 2 and 2 because that's what we're asked to do right here in the problem. So x equals 2, y equals 2. The good news is we can just copy this code and just change fx val to fy val. And we're just going to substitute for fy instead of fx. So that's pretty cool that we can do that pretty quickly. Now that we have the derivatives and the values of the derivative at the point 2, 2, now we can go ahead and build the equation of the plane. So the plane is going to be equal to, now we have to get z0, which is going to be where we substitute back into z, xy, And we're going to insert the points 2 and 2 back in there. All right, so that's our z0 plus our fx val times x minus 2. So that's, remember, x minus x naught. In this case, x naught is really 2. And then we're going to do the same thing. We're going to have the fy val, and that's going to be at y minus 2. Right? We're going to plot our plane. So we can, and also the function. So let's just easy plot z. We're going to hold, and we are going to easy plot our plane, and we're going to hold off. All right, so let's give it a whirl and see what happens with this. I put x plot instead of easy plot, so good thing I caught that beforehand. Just scanning over my code really quickly, and let's give it a run. And something doesn't like here. So invalid indexing must be followed by. All right, so it's not even telling me which line, which could be hurtful, except I think I might have figured it out. I think I forgot the multiplication right here. So after another quick scan, there we go. Okay. And I should have done easy surf instead of easy plot. All right, so let's try one more time. So sorry about that. Let's run. All right, there we go. Now, I didn't define any of the variables, or I didn't necessarily define what the domain would be. So even though we get like this tangent plane to this surface, we could certainly zoom in and we could start seeing exactly where it's tangent at. All right, and if we tilt the graph just right, we could start seeing it. All right, now if we really wanted to, what we could do is we could just change the domain from 2 to 4, or from like something like maybe 1 to 3, and then from 1 to 3. All right, for our easy surf function, and then we can just copy that. And again, we do 1, 3, 1, 3 because we're trying to see what's going on around 2. All right, so let's go ahead and run this. It might give us a better picture, it might not. All right, and that's what we get out of it. All right, we could see the tangent plane, we could see the function. All right, so right there is a pretty good angle at which we can see the cross section of the plane. This is supposed to be a hemisphere, but I think with the graph, it just accommodates. And then you can see right there where the tangent part is. It's pretty cool that you can see that through there. So, I mean, again, if you want to zoom out, you can just click on the graph, and I can just roll the graph around a little bit to be able to zoom in and zoom out. All right, but pretty neat that we're able to find the equation of the tangent plane, which is going to be 9 minus 2y minus 2x, but also be able to graph both the surface as well as the tangent plane on the same graph. So we're going to have one more video in this series, and what we're going to do is we're going to be able to find the critical values of functions in 2 variables by using MATLAB.